cool trick. I like this trick. Let me show you the trick. Let's say you have the square root of 9 minus x squared over x squared dx, and we want to solve this. You can make almost any substitution you want as long as you follow through. So this substitution, I'm going to let x equal 3 times sine of theta. Taking the derivative, I'll get dx equals 3 cosine of theta d theta. So let's plug that in. X squared will be 9 times sine squared of theta. X squared, again, will be 9 sine squared of theta. And your dx becomes 3 cosine theta d theta. Now let's work on simplifying this pup. I can factor 9 out of the numerator, out of both terms. And when it comes out of the radical, it becomes a 3. And then I have a 3 over here. So between the two of them, I'll have a 3 squared, which is 9 over 9. I'm doing too much in one. I'll have 3 times the square root of 1 minus sine squared theta over 9 times sine squared theta times 3 times cosine of theta. Oops, d theta. So what can I do? Well, here's a 3, there's a 3. 3 times 3 is 9. It cancels with that 9, so my constants are gone. This is cosine. This is, now look at this. I have the square root of 1 minus sine squared theta. But 1 minus sine squared theta is cosine squared theta. And the square root of cosine squared is just plain old cosine. So this expression here becomes cosine theta. And I have cosine theta here. So now this becomes cosine squared theta over sine squared theta d theta. So that's a little bit nicer. Let's see, cosine squared over sine squared, they're even. Oh, I don't want to use that whole half trick rule. I'm going to rewrite this as, let's see, cosine over sine is cotan. Can't integrate cotan, so I'm going to use the same trick I used with tan squared and rewrite this one using the Pythagorean identity. So cotangent squared of theta is cosecant squared of theta minus 1. Try to run off the page. The integral of cosecant squared is negative cotangent. The integral of 1 is theta. Yay, we have our integral. Except the integral is in terms of x's, my answer is in terms of theta. I need to use my substitution and go back and figure out what this is. So let me look what I have up here. Let's go back up here. Up here I have x equals 3 times sine theta, which means sine of theta is x over 3. So drawing my little handy dandy right triangle, I'll make this theta. The sine of theta, which is opposite over hypotenuse. So I have a triangle that fits this situation. Using the Pythagorean identity, we're using Pythagorean a lot today. I get the square root of 9 minus x squared. Cool. So down here, cotangent is adjacent over hypotenuse. So, sorry, adjacent over opposite. So this becomes, reading the triangle, becomes 9 minus x squared over x minus theta. Well, if sine theta is x over 3, plain old theta is sine inverse of x over 3 plus c. Oop, do you guys see it? Isn't that a cool trick? I like it. It's a very cool trick. Now, other substitutions we can do. So this one was basically we had an a squared minus an x squared. So we were able to use the sine squared plus cosine squared equals 1 deal. So I would let x equal a times sine theta. Other possibilities. If I had an x squared plus an a squared, here I'm going to let x equal a tan theta. Because when I put it in here, I'll get a squared tan squared plus a squared. So when I do the the simplification, I'll have, let's see, a squared tan squared theta plus a squared, which will simplify to a squared secant squared theta. Oop, off the page again. Yes, I live near a train. The other possibility is I could have x squared minus a squared. And in this case, I'll let x equal a secant theta. So my x squared minus a squared will simplify to a squared times tan squared theta. Is that right? Tan squared? Yes, it is. Oh, sorry, it took me a second. Okay, long dead space. So that's how you do the other substitution. Let me do one more example. We're at 6 minutes. I don't want to make this too long. So how about I try the integral of dx over the square root of x squared minus 9. The derivative of the bottom is not sitting on top, or the derivative of the inside is not sitting on top. I might actually be able to do this easier with a substitution, but with a regular substitution. But since I'm in this trig sub, I'll do that here. I'm going to let x equal 3 times, this is the secant theta. So dx is equal to 3 secant theta tan theta d theta. My integral becomes, too many dx's, 1 over the square root of x squared, which is 9 secant squared theta minus 9, times my dx, which is 3 secant theta tan theta d theta. So let's see, I can pull a 9 out of the bottom. When it comes out of the square root, it becomes a 3. I get the square root of secant squared theta minus 1. And on top I have 3 secant theta tan theta d theta. Now remember, let's make this with red. This is equal to tan squared theta. So the square root of tan squared will be tan. So this guy will cancel with that one. And the 3's will cancel. So I'm left with the integral of secant theta d theta. And oh boy, I have that one memorized. The integral of secant theta is natural log of secant theta plus tan theta. Go back to my triangle. Go back up here. I know that x equals 3 secant theta. So secant theta equals x over 3. Doing my handy dandy triangle. There's my theta. Secant is 1 over cosine. So if secant will then be hypotenuse over adjacent, making the third side x squared minus 9. Reading secant and tangent off the triangle, or just what I have there. Secant theta is x over 3. Tan theta is the square root of x squared minus 9 over 3 plus c. And this will simplify to that. So 9 plus c. Do you know why? Figure it out, because that would be a good question somewhere. Okay, so that's how we do substitutions, the other trig substitutions. Make sure you don't go trig substitution crazy. Now what I mean by that, if you see something like this, the integral of x over the square root of x squared plus 9, don't go, oh, I'm going to do a trig sub. This is much easier if you do a regular substitution. You would let u equal x squared plus 9. du is 2x dx. This becomes 1/2 the integral of u to the negative 1/2 du. Much easier integral than going through all the trig stuff. So look for the easiest way of doing it, and if all else fails, and you have the situation, you can try trig sub. That's another cool trick. And that's my trick. Oh, did you see it? Yep.